Okay, so we're deriving Cartesian equations of paths, and we do this after we've been given a vector equation. This video is going to focus on paths that are elliptical and also hyperbolic, i.e. they make a hyperbola. So we're going to do two examples, one of each, and in both examples we're going to do the same thing. In yellow you can see there we're going to find the Cartesian relation that represents the path of a particle and find its domain and range, do a sketch of the graph. Then in part two we're going to give the starting point of the particle's motion, the direction, and if it's repetitive we're going to state the period. Okay, so for the given vector function r of t that you see there, we're going to now generate the Cartesian relation. Note that t is only 0 or positive, and we need points x and y. So let x, y be any point on the path. Alright. And that's what a Cartesian equation generates. It's a description of the path of the particle. So we come up with parametric equations, which I'm writing down now, that link x to t and y to t. So those are derived from the given vector equation. Now we do a rearrangement, and the reason for it will become apparent very soon. So we've got negative x on 5 equals cos pi t over 2, and we've got y over 12 equals sine pi t over 2. Now these sort of situations usually involve a trig substitution or a trig identity in particular. So this one will be the Pythagorean identity. So there's the Pythagorean identity there, sine squared a plus cos squared a equals 1. In this case, a, the angle, or the real number, is pi t over 2. So because our parameter a is the same in both cases, i.e. it's pi t on 2, we can use that identity. So instead of having sine squared a, we would have, which is the square of the right hand side here, we would be able to substitute y over 12 and square it. Likewise, instead of having cos squared, we can have negative x on 5 all squared. Like so, we can see, and evaluating that, so we have x squared over 25 plus y squared over 144 equals 1. Now that is the relation for an ellipse. So we have an elliptical path, and we can read from this equation some of the features of that ellipse. So our parameter a equal to 5, b equal to 12, and that means we've got an ellipse, which I'm going to attempt to draw. Ooh, not very good. With its major axis going vertically. So it's got more of an elongation away from the x-axis in the I direction than it has elsewhere. So that means it has x-intercepts negative 5 and positive 5, and y-intercepts 12 and negative 12. It also means we know the domain and the range. Okay, so it's negative 5 to 5 inclusive for the domain and the range. Negative 12 to 12 inclusive for the range. So for the starting point t equals 0, we find r of 0, which we get negative 5i using the vector equation, which corresponds to the point 5, 0. You can see just up there, and then it moves around. So that's the starting point. That's one of the things we had to find. And moves around. Let's use a subsequent time that's easier to calculate. T equals 1, and when t equals 1, we've got r of 1, that comes out as 12j, so that corresponds to the point 0, 12. So it's gone from there to there, and that means that its direction of movement is clockwise. It's important to note too that this is a this center of this parabola, of this ellipse, is at the origin. Okay, it's one of the ones centered at the origin, which affects the equation. So the h and the k will be 0, so they drop off. Last thing I have to find is the period. So it is periodic. We have t is 2 pi over b, and you can see from the given equation the parameter b was this part here, which is pi on 2, and that equals 4 time units when the b parameter is pi on 2. So let's move on to the second example now, which is just here, and we have to do the same with this one here. Now it looks different. It hasn't got sine and cos, it's got tan and sec. So is there a trig identity we can use? Yes, there is. Using our formula sheet, we can see that there is one, and it's the second one there. We've got tan squared, that one there that I'm trying to highlight. Tan squared a plus 1 is sec squared a, and we'll just rearrange that to get the 1 as the subject, and we can see that there. We're going to use that in a minute. So we've got x, y, again any point on the path, and you can see we started to rearrange on the left hand column there, so we can use that substitution like we did in the previous example. Because the identity involves squaring, so we square them, as you can see, and in this case a, the angle or the real parameter, is pi t over 2. So instead of sec squared pi t over 2, we have the following, and minus, instead of the tan squared pi t on 2, we have, by the way, that little squared sitting a bit high there, it makes that a bit more obvious. There we go. So we have that there, which is a type of hyperbola. Because it's in the form of y squared minus x squared and not vice versa, it's a special feature about this hyperbolic path. And because it's y squared minus x squared and not x squared minus y squared, the orientation means that what's called the transverse axis is vertical. Now the transverse axis is something that runs through the vertices. Let me explain by illustration. And by the way, this is a hyperbola that has its center at 0, 0. We might as well get that detail out the way. It's centered at the origin, so that's fine. That makes life a bit easier. So the two branches will go like this in such a case. Okay, the transverse axis runs through the vertices, so ones that are centered around the origin, the vertices are also the intercepts on the y-axis. Alright? Now because they're both the vertices and the y-intercepts, we have to find the y-intercepts, and the y-intercepts happen when x equals 0 as ever. So we have 1 equals y squared over 9, and x is 0, so that second term is knocked out, and we have 9 equals y squared. So we have y equals plus or minus 3, which makes sense. So we have negative 3 and 3, so it's 0, 3, and 0, negative 3 for the two ordered pairs there. This question has an extra level of complexity. We have to consider the given interval for t, so t, or the domain for t, time, not x, but t for time, is from 1 to 3 exclusive. So we need to look at the behavior of those things for x and for y. Now, this takes a little bit of thinking and a little bit of help from technology. We know that with the help of technology, like a graphics calculator, you can work out, and plus your knowledge of tan, we know that tan pi on 2 is undefined because it's 1 over 0. Same with 3 pi on 2, our knowledge of the unit circle and so on. But we can use our graphics calculator to work out those two limits. It's undefined, but that's alright because it's an exclusive domain there. It's defined between that, and we can use a graphics calculator or Desmos. Okay, we can see that within those limits it's perfectly okay. So provided we stay within 1 and 3, and that's fine. So for the interval we're looking at, it's defined for all real numbers. So for all intents and purposes, the domain is fine for all real numbers. What about the range now? So we look at the two limits for t, and we also look at what happens between those. A bit of technology helps out. So for you can see on the edge of the screen that we got the shape of sec x. Remember, it's the reciprocal of cos x sec, and if I just take it back to regular sec, it has its minimum limits on the above the x-axis is 1, and vice versa below the x-axis it's -1. But we've actually got -3, so it has that effect on it. So you can see that it goes down to 3 and -3 on the other side. Now we know that if we have just well, we might not know, we can use technology to show that it's undefined at the limits like the other function was. But if we look at either side of the limits, so if we go a little bit higher than 1 pi on 2t, if we go a little bit higher, it starts to have a value again. Alright, it's asymptotic perhaps. Alright, and you can see that it gives a value there. And same with 3, we know that for 3, but if we go slightly less than 3, within 3, so 2.99, there you go. So it's got some values. So and you can, if you look at your graph and move things around, you can see that it will be continuous between that. So the thing is, within our domain, between 1 and 3, which you can see here and here, it only considers the values from 3 and above. So all those negative values drop away. So looking at values that are at and between the limits of the interval, we can see that it's only the top branch. So if we sketch it, it will be basically, we found out it was 303 here before, and it'll only be that one, and it'll just trail up there. So all x values between 1 and 3 are fine. Sorry, not all values between 1 and 3. For x, all values are fine. Okay, within the parameter for t was given, but for x, all real values. For y, it'll only go down to 3, and it'll go up to positive infinity. So the domain and range can be written. It's only the top branch, so that leads us on to the domain and range for the actual curve. So domain, again I'll write that it's all real numbers. The range, is from 3 inclusive up to infinity exclusive, of course. In terms of the starting point, because r has no limit, it just keeps going. There's no actual starting point. Okay, it's not periodic, it's not repeating at all, and if you look at the endless nature of that upper branch, it's not going to repeat. Okay, and the functions you might know from your previous knowledge, tan and sec don't repeat in a periodic manner like sine and cos do. Okay, so there's two ways you can tell that there's no period. Okay, it's not periodic, and the particle moves from left to right. You can see that by putting in some subsequent times. It doesn't have to be those times there. We get that position first, and then we've got an increasing I value as we go. It increases from -4 to 0 up to +4, so that's showing that it's moving to the right, and we can see the corresponding values for j, vertical j, so it's going down then back up because of the branch effect, but it's moving from left to right.